Okay, we are at section 30.5, direct current generator, or a DC generator, what we call a DC generator. And before I share the PowerPoint, I'm going to go to our old friend Walter Fent to demonstrate um, the DC generator. Now, if we were to let's get this and pause it. Um, Now, there's charges. There's electrons and protons in the wire. So let's do our right hand rule on this. We've got the I'm putting my fingers in the direction of the blue magnetic field, and I've got my thumb in the direction of the uh, the motion of the wire. So which way are the positive charges gonna go? They're gonna go to the palm of my hand, and notice that's the direction that the red arrow is in. We can do the same thing with the bottom. Uh, I'm gonna have to contort the magnetic field is going downward. The velocity is this way, and uh, the positive charges are out the palm of my hand. On the bottom loop, the red loop, you can see the current is going um, to the left, and on the top it's going to the right, which follows our right hand rule. Now let's resume this. So as this, what are we changing here? The magnetic field's not changing, and the area of the loop isn't changing, but we have the theta changing. So we know that d phi dt is equal to d dt of BA and cosine theta. So the B is staying the same, the area is staying the same. It's only the angle that's changing. And sure enough, it creates uh, this current in the loop, and you can see that it produces a sinusoidal wave. Now we introduce this as calling it a direct current generator. So I mean, you can see that there's a hand crank. There's a hand crank here. So somebody's cranking this thing, and it's generating um, generating. That's why they call it a generator. It's generating an electric field. Now you can do this. You can use wind power. Wind will you turn a turbine, and the wind will move a loop through a magnetic field, and you'll get electricity. You can do it with water power. The water turns turbines, and that generates electricity. If you've ever been to Hoover Dam, Boulder Dam, whatever you want to call it, that's how it is. You hydroelectric power. Now, let's go back to the DC part of it. We put a commutator in there, and you'll see that every time um, you turn it, it switches uh, it switches the direction of the current, and so that it's always positive. So that you rectify that, and you'll get direct current. We'll talk about rectification later. That's using diodes, but you can see that it's all positive. Okay, now that we've done that, let's change our share. Let's see, let's do a new share and go to the PowerPoint. And now we see exactly what Walter Fent was showing us. We've got this little loop connected to brushes of a commutator. And as it turns, it induces uh, this rectified, that means only positive, sinusoidal waveform shown in B there. Let's see if there's anything um, uh, that I missed. Yeah, commercial DC generators use many coils and commutators distributed so that the sinusoidal pulses from various coils are out of phase, and so that you reduce the fluctuations. Okay. Um, Now, an alternating current, that's what we showed you uh, at the beginning with the Walter Fent. That's where there was no commutator. So it produces an alternating current, just a sinusoid. You could see that on if you didn't see it, we can go back and look at the Walter Fenton, you go back to it without commutator, you'll see that the little waveform up here is sinusoid. With the commutator, it's all positive. So let's go back and to the PowerPoint. Here we go. All right, so with without the commutator, you get the AC generator. Now here we've got the coils going through the magnetic field. Oops, wrong way. And so phi is equal to B A cosine theta. Well, B is equal to A cosine omega t, where omega is the angular velocity, and t is the moment in time that you happen to catch it. And so E is equal to the minus n, the number of turns, d phi dt, the changing magnetic field. So that's equal to minus n BA. Remember, the magnetic field's not changing. The area is not changing. So all you have is ddt of cosine omega t. So the induced, the EMF is equal to NBA omega sine omega t. The derivative of cosine omega t is omega sine omega t, and that's where they get that from. So the ddt cosine omega t is omega sine omega t. So the E is equal to the number of turns times the magnetic field times the area times omega sine omega t. Since it varies, let's see why. Let's see. The maximum occurs when omega t is equal to 90 or 270, and it varies sinusoidally with time. So the induced EMF in the coil is just NBA omega. Well, that's the E max, and the E max occurs when sine omega t is equal to 90 or 270. So that's the max. That gets rid of the sine omega t. Okay, and let's see. An AC generator. In an AC generator, a coil with n turns of wire spins in a magnetic field. One of the following choices, which does not cause an increase in EMF generated in the coil. Replacing the coil with one of lower resistance, spinning the coil faster. Remember let's go back to the equation. Oops, I just gave it away. Let's go back to the equation. E is equal to NBA omega. So replacing the coil wire with one of lower resistance. Nowhere in there does it show anything about the resistance. Spinning the coil faster. Well, oops, wrong again. Omega is faster if you increase omega. E increasing the magnetic field. Well, if you increase B, E max goes up, increasing the number of turns of wire in the coil, and certainly you see there's N there. So the answer is all of these would do it except replacing the coil with one of lower resistance. I think we'll go ahead and, let me look over here. That'll tell me whether, yeah, this is one section, generators and motors. Now motors, here's a cutaway of a motor, and it's kind of just a reverse of, let me see if Walter Fenton, we'll just take the time and look and see if he generated. Here's a DC current or electrical motor, there's no hand crank, and it just the This is from the torque. You remember if we put a current in a magnetic field, if we put a loop in a magnetic field, it induces a torque. Well, we take that torque and apply it to some kind of drive shaft, and it'll drive a motor, and that's what we have with a DC motor. Let me go back to see if there's something I skipped with the motor, and so it's just an energy transfer of electrical transmission into a motor. The energy is transferred out by work. It's basically a generator operating in reverse. Okay, so mechanical work is done by attaching a rotating coil to some external drive device. As the coil rotates, the changing magnetic field. Well, that messed up. Anyway, so basically motors are generators in reverse. And next we're going to talk about eddy currents. That shouldn't take long. Let's go ahead and stop the share. And